And welcome once again for another episode of Profiles in American Funded Research. I'm excited to have my guest today, Lis Gallant. And Lis did a bachelor's degree at Rensselaer Polytechnic University, another bachelor's at the University of Buffalo, SUNY Buffalo. She got a master's degree at the University of South Florida and did a PhD at the university, also at the University of South Florida, and is currently at the University of Hawaii. Is that correct?
Yeah, there's a couple of postdocs sprinkled in there too. And for my bachelor's degrees, there's actually several universities in Buffalo. And so I went to Buff State College and not UB.
Oh,
It's
not
the,
UB. Okay, I
yeah, it's a
apologize.
different beast. Ah, no worries, no worries. They have more funding, so that would have been great. No such luck though. We made it through.
And I know that you have a variety of funding, so you were I wanted to give you an opportunity to just kind of describe that rather than focusing on a single project in this case. So I'll let you get started on that.
Yeah, I guess the reason I'm here is because you originally reached out, right? Because I had an NSF funded postdoc that was kind of closing the gap between, computer-based lava flow models. I'm a volcanologist. That's why I am in Hawaii now. And so closing that gap between computer-based models and analog models. And so I had applied for this National Science Foundation postdoc in the before times, before COVID. And then I had ended up getting a different postdoc at the University of Cambridge. And so I moved to England March 1st of 2020. It turns out the timing on that was a non-ideal situation, but we do what we can. And then partway during that postdoc, right, the work we were supposed to do involved a lot of international travel, and so that kind of did not end up coming to fruition. And so I was offered the opportunity to take this National Science Foundation postdoc, and it was just a better fit for me and my family. And so originally, right, I had written this postdoc to do some analog modeling. So that would have involved me traveling to England to do some other work. And right, I took this postdoc during the pandemic when travel was decidedly more difficult. And so I had to pivot a lot of the work I had planned to do in taking this postdoc, which is why I want to talk a little bit more about what I did with that funding as opposed to a singular project.
That that sounds great. Um, can you give a description of what it is that you did? A brief one?
Yeah, so I am, right, I'm a volcanologist and I like to study the different ways that lava flows and volcanic vents impact the surface, how they propagate, how we turn that into, something that we can use in a forecasting tool, kind of like a weather forecast, but for lava. And so one of the things that I did with my National Science Foundation postdoctoral research fellowship was actually to bring a lot of collaborators out to Hawaii so that I could do a variety of different projects as they kind of cropped up. Right, I had initially written this project to look at lava flows from the 2018 eruption of Kilauea that impacted a lot of people in Lower Puna. So I live on the Big Island. It's not the one with Honolulu, and we had a fairly large eruption, the largest eruption in 200 years, that happened in 2018. It impacted, I think it claimed over 716, structures, that kind of stuff. And so I'd originally written work to study that, and I ended up using my fellowship to continue to study that. But I brought out some collaborators to study how the vents formed, right? So when we have a volcanic eruption, it's not just like lava is falling out of a hole, like the hole manifests itself and then the lava falls out, right? We start off our Hawaiian eruptions as these kind of linear structures, these fissures, and then we build these volcanic piles around them. And so understanding how those piles grow helps us understand how we can build that kind of behavior into a lava flow model, right? Because as you're modifying the landscape around you, you can think of a lava flow effectively as a flood that doesn't, it still maintains some height. And so as you imagine a flood, right, it's filling in the crevices and the cracks. Well, if you're building a mound around the area where your flood of lava is coming out of, you're modifying the landscape and you can't use your old topography, so your old ground to model a current flow because you've changed it already. And so what you're using is obsolete. And so I wanted to understand how we could build models of cone growth. And so that's still kind of an in progress feature. And another thing I did is I responded to like a lot of eruptions during my postdoc at the Hawaiian Volcano Observatory. Right? There was an eruption that started kind of before I came here in 2021, but I got to respond to the tail end of it. So that was the December 2020 eruption. I responded to the September 2021 through December 2022 eruption. I responded to the Mauna Loa eruption in December or November and December of 2022, responded to the January 2023 eruption, and then finally I helped do some response as I transitioned out of my postdoc at HBO into my role as an assistant professor here at the University of Hawaii at Hilo. And so a lot of what I did was pivoting kind of away from that 2018 eruption into just the fire hose of new new data that we could collect as we transition from that eruption to our new eruption, which is kind of ongoing, the summit eruptions and a couple of rift zone eruptions. And so, yeah, I have mostly just responded to what has been erupting in front of me kind of towards the end of that funding period. And so because of the dynamic nature of living out here, I had to switch gears a lot because when the volcano is erupting and you work in an observatory, you have to respond to the eruption. And so a lot of the subsequent work I did included using some novel radar techniques to observe what we could using let me step back there because my brain just fell out of my body for a second. So another thing that we did was we deployed a lot of novel radar instruments. And so you can think of radar, right? You have weather radar, you have satellites, and satellites are really great in volcanic situations for, you know, checking out the lava without being too close, but you don't always have the same repeat interval that you need to kind of keep a good eye of what's going on. And so we deployed a couple of experimental radar to see if we could use those for monitoring purposes. And some of that stuff is now submitted to journals and going through the Plinko board of review. And so instead of doing the original plan, I made it a little bit more robust and branched out into a lot of areas.
Awesome. Thank you for the introduction.
Yeah,
So
that wasn't quick, but it was an introduction. So there you go.
well, it was quick. It was definitely quick enough. Um, so it sounds like just to make 100% clear that you're modeling the flows. You're going to try to predict where the flows go, right? No. So you're not trying to predict an eruption. You're trying to predict where the flow will go.
So I did a lot of that kind of work, lava flow modeling. Like I developed some vent openings. So when you think of a volcano, right? If I was to ask you to draw a volcano, you would absolutely draw me a triangle with some stuff coming out of the top. A lot of volcanoes don't erupt like that. And so sometimes you'll have a vent. So I'm just going to use the word vent to describe any place where lava comes from, a vent popping up around either these distributed volcanic fields. So I did a lot of work on the modeling itself for my PhD, but now I'm kind of transitioning away from that uh, to more data collection to help modelers, right? Because I have access to active eruptions in ways that people that are not local residents, it's very difficult to kind of fortuitously deploy your instruments and collect your data if you're not here all the time. And so I transitioned more into kind of data collection for the purposes of improving models.
And when you're because it sounded like you're responding to all these volcanic eruptions in order to collect this data. So when you're doing this, are you localized to Hawaii, or are you going to other volcanic eruptions outside of, say, the US?
I have in the past. Right now, the nature of where I'm at, right? I'm not at a high-powered R1 research institution, although the ability for those folks to do that kind of work is rapidly reducing at this point too, with recent funding cuts and such. But no, I have one of the world's most active volcanoes literally in my backyard. Like when it erupts, I can see the glow from my house at night.
Oh,
And
wow.
so I have that's the resource I have available to me. It's what people, write these grants to come do. They write grants to come work in my backyard. And so I am kind of opportunistic in that I have what so many people are, writing grants and going after funding opportunities to get access to. Like, I don't need to do that. It is in my yard. And so I generally have pivoted my focus there, but in the past I have responded to kind of unrest and eruptions in both Nicaragua and a bit of unrest in El Salvador and Colombia as well. And so I have in the past, but it's not been something that has been a big piece of my current academic research scientist life.
Are are you at a like a primarily undergraduate institution or okay.
Yep. And
So
actually a
do you
lot,
have
oh
students
yeah, sorry.
working with you?
We absolutely do. And so one of the things that I think is was one of the big draws for me to take this kind of job was because we have a lot of local students who, right, UH Hilo is not like the flagship institution for folks that aren't familiar with how it works, right? I went to Buff State College. You're like, oh, UB. There are one institutions in these state school kind of systems, and those are the ones that do the flagship research and all the money. But very often there are supporting kind of regional institutions that are primarily undergraduate, as well as community colleges. And so I went to a lot of different universities, and I think I got the best education at a primarily undergraduate institution. And so I wanted to work at a place like that. I wanted to provide students like me uh, with research opportunities in ways that they might not be getting if they're going to a place that has master's or PhD students. And so I'm at a primarily undergraduate institution. We hire our students into kind of the eruption response sample process. And so when you see data coming out of these eruptions, like the chemistry data, the students here at the University of Hawaii at Hilo are some of the folks who are processing that data. They are the ones, crushing the lava samples, running them through our EDXRF, which is just something that gives us our chemistry that helps us track. We think that the lava is being sourced from these locations, or it's heating up, or it's cooling down, that kind of stuff. And so our students are integrated. They're not just, on the side, they're integrated into the eruption response process here. And we also are extremely fortunate to have our colleagues at the Hawaiian Volcano Observatory working alongside the students as well, because they're obviously driving the train, right? Eruption response is inherently their kuleana, their responsibility. And so we have a pretty fantastic integrated lab team that includes like the faculty here, the staff here, the students, and our USGS, HVO kind of partners.
Now, what kind of data are you collecting? Because I think you mentioned a little bit with the what you were having the students do. You also maybe mentioned topography, potentially these kinds of things. What kind of data are you looking to collect?
Whatever data we can. No, that's why when you initially approached me, right, I was like, I don't know if I can talk about one project because I'm definitely kind of an opportunistic scientist, right? As a person who has access to the really dynamic landscape on a pretty consistent basis. If something changes and we have the opportunity to collect, radar data, so to get, deformation changes, or if we have the opportunity to collect more um, ground-based data. And so I collect all sorts of data. When I think about scientists, right, there are folks that I work with that are really specialized in instrumentation. And then there are folks who are specialized in processes. But then there are the oddballs like myself who are just like, I just like volcanoes and I live here. And so if this cool thing shows up, yeah, we'll deploy it. We'll see how we can, leverage it for operational research. And so I really struggle to define exactly what I do in a really narrow, in an easy and concise way because it's always changing. And so during the Mauna Loa eruption, actually, I'll backtrack. So when I was in grad school, I used something called a terrestrial radar interferometer. I've been trying to image a lava flow with this thing for like 10 years. And so that is just effectively, if you have two eyes and you have visions in both of them, if you close one and you close the other, you have a slightly offset image, right? And that's what creates 3D topography in your brain. That's what gives you your depth perception. Well, you can use these instruments to kind of scan the landscape and do the exact same thing. And very often, right, if we're building 3D maps, like, all right, I got the land, I scanned it once, it's not changing, so job done. When you have a lava flow and placing into an area, your landscape is constantly changing. And so we do this every minute or every 2 minutes or every 5 minutes. And so I have been trying to get that instrument pointed at a lava flow that's been moving since 2015. And so showed up to Nicaragua, the Momotombo eruption stopped. My colleagues had tried to show up to Pacaya in Guatemala, and the eruption stopped. And then they showed up here during the 2022 Mauna Loa eruption, and the eruption didn't quite stop, but it definitely, the tap turned off a little bit. We did collect some data that indicated we were able to image a little bit of the shifting of the lava flow on the side. And so this, if you ever want to shut down a volcanic eruption, let me know. I have the right instrument for that. But because the instrument was on island, that January 2023 Kilauea eruption that I talked about, we were able to image deformation of the lava lake surface with that instrument. And so I think it's going through review at this moment. So I think we're the first folks who are able to actually capture kind of larger scale deformation of like a lava surface with that. And so we're going to use that to kind of feed into different models as we tease out what the data can and cannot tell us. And so that's one thing that we collect, right? So it's how the surface of a lava flow changes, or in this case, a lava lake, with that instrument. Unrelated to that, other than the fact that it's an active volcano, we're also collecting, right? Our USGS counterparts are collecting samples, and we want to know what those samples are telling us. In 2018, the folks who were are still at my institution, right? They'd get a sample every day, they'd run some chemistry on it, they would get information about, what the lava was doing. And so when we're looking at geochemistry, Hawaiian lavas are relatively straightforward, super into that, nice and easy system. And so we have, right, mineral called olivine or peridot. If you are a child of August, it is your birthstone. And so depending on how much, magnesium or how much iron it's using, right, those magnesium versus iron will get integrated into our olivine at different temperatures. And so if you have like a high magnesium reading from your geochemistry, like that tells us like, oh, those, that packet of lava probably has magma that was stored in this area, or, that's a higher temperature flavor of the olivine. And so we expect that the lava is hotter, even though we're not necessarily getting the temperature as it's coming out of the tap. And so those changes in some of those important elements like magnesium versus iron, like that'll just tell us things that we can use to then infer behavior, right? A hotter lava will flow kind of faster in a more fluid way, and the way that you might want to model that is fundamentally different than if you had like a slower, stickier, more sluggish lava. And so we're working with the USGS folks to get, right, that kind of consistent data set of, all right, we have a sample, we'll run it. Here's what the lava, looks like in this sort of way today at this moment in time. And so the folks here who are at the University of Hawaii at Hilo before me, they're the folks that really pioneered that kind of near real-time lava flow geochemistry. And now it's become a pretty standard approach in places like Iceland, in places like the Canary Islands. Piton de los Fornes is starting to incorporate some of the near real-time approaches in a similar sort of way. I mean, they have a variety of different things they're doing down there that's super cool, but right, it's becoming kind of an expected thing that you have to do for these basaltic eruptions, because even small changes in the temperature can have a big impact on how or where your lava is going to flow.
Now, what you mentioned that it's easy or straightforward or something in Hawaii, the eruptions. What makes other places different? What would make that?
I mean, that's an oversimplification, but when you're thinking about the different kind of minerals that you have as your kind of stopwatches or your clocks, olivine is a pretty well studied one here in Hawaii. And so this is a situation where when we think about places with eruptions, right? Hawaii is one of the places that comes to mind. And so there's a wealth of historical data. And so we've been able to dial in within a couple of degrees. Like if we have, if our olivine has a ratio of that magnesium to iron here, that's telling us we're going to have this kind of temperature. And again, it's an oversimplification, but I assume that not everybody in your audience is, you know, up to snuff on their volcanic petrology. So,
And I what's different about other places though? So it's just the
oh,
mineral
okay.
composition? Yeah.
So yeah, I think of lava as I'm pretty much the hungriest person you'll ever meet, constantly food on the brain. And so I think of lava as kind of a spectrum of chocolate, right? You have dark chocolate, you have, maybe a milk chocolate, you have a cookies and cream, and then you have a white chocolate. And so Hawaiian lavas are kind of like our dark chocolates in that they have low silica content. And so if you think of silica as sugar, right, you have higher sugar in that white chocolate. I still like it, not everybody does, but it's got a time and place. And so places that have a higher silica content or, the white chocolate kind of lavas are more likely to explosively erupt. And so that's what's driving a lot of the behavior. And so our lower silica content lavas are not necessarily unlikely to explosively erupt. We've had explosive eruptions in Hawaii in the past, but they're a little bit less dynamic in the styles of eruptions we might have. Places like the Andes kind of have that mid, like that milk chocolate to cookies and cream kind of lava. And so you can get some kind of big sluggish lava flows there. You can get eruptions that are explosive and dynamic. In kind of the last 20 years, there have been some large eruptions down there. And so it's just a little bit easier to manage the system because when we are thinking about volcanic petrology, there's like a certain order at which things will solidify. If I have a giant box with all of my lavas and I start cooling it down slowly, we're going to get olivine first and then we're going to get plagioclase. And so there's this whole thing called Bowen's reaction series. And so we are starting at the top of that here in Hawaii. And so it's a little bit easier to kind of understand the progress because we are starting at the top. And so we're only dealing with those kind of higher temperature minerals instead of having to worry about kind of oscillations. Well, it started off as a really hot lava and then it kind of sat there for a while. We do have that in these small little packets, but it's generally not a thing that's driving a lot of our eruptions. And so it's not that it for us it's easier because we have the historical data, because the system has been one of the best studied on the planet. And so and because right, we're specialists here. We are place-based education. We are focusing on the volcano in our backyard. And so it's a lot more familiar for us in a variety of ways.
Does the explosive type of eruption, does that have a different kind of flow? Would you model that differently, the flows that come afterwards from
So
a less explosive one,
so
for one
yeah,
that's explosive?
no, it's one of those situations where I didn't, oh, volcanoes, right? Some of them explode, like Mount St. Helens, and some of them don't. And so, very often, if you'll have an explosive eruption, like a bigger, like Mount St. Helens, that kind of thing, or Coronacaye, which is down in Chile, those may often be followed by these really slow, sluggish, low gas content um, more felsic. I'm just going to use the word felsic. It's, the more white chocolatey, cookies and cream kind of lavas. And so what happens, right? Your lava isn't always lava when it's underground. It's magma. A lot of people will tell you, oh, if it's above ground, it's lava. If it's underground, it's magma. But I think of it more in terms of phases. So before our lava turns into lava at the surface, right, it was magma and it had gases, liquids, and solids. And so if you have a really explosive eruption, your gases are what's going to drive that eruption. And so you're left over with the liquids and solids. And so you'll tend to have these really thick, high viscosity, really, kind of sluggish lava flows. And so for those of you who've ever been out to Oregon or, the Pacific Northwest, those obsidian kinds of lava flows, those really kind of glassy, really thick, super, super tall lava flows. Like that's what you might expect after an explosive eruption. Here in Hawaii, right, we are not explosively fragmenting our magma as we're kind of decoupling the gas from it. Not always, though. Sometimes we do. That's a different beast. But as we're doing that, we are kind of degassing our lavas in uh, a little bit. And so we're doing that without kind of violently bringing the entire system up with us. And so we are not necessarily seeing those high volume, high explosive eruptions here in the same way that you would in other places. Another thing that kind of factors into it is our tectonic setting, right? The Earth is a soccer ball with plates. This is an oversimplification, but we're plates kind of not floating around, but moving around on the surface. And so our places with more explosive eruptions tend to be at our subduction zone. So you have a plate that is kind of getting sucked underneath an overriding plate. And as your magma is kind of chomping its way through the overriding plate, it's collecting, right, bits of that plate, and that's changing the flavor of the magma, and that's bringing in more volatiles, which is driving more explosive eruptions. And so Hawaii, different beast out here. It's pretty much we just blow torching straight on through that crust. And so we are bringing our magmas up kind of directly from the mantle. Sometimes they hang out in little chambers here and there, but we are sourcing at ours is a more pure magma, if you want to be that way about it. Ours is more similar to mantle composition. And so the mantle is kind of built more like Hawaii than it would be like Mount St. Helens.
And that difference in composition does affect the flow. Is that I wasn't
Oh,
sure.
absolutely. Yeah, so if you have more silica, more sluggish flow. You're going to have a thicker flow. Although if you have more silica, you're less likely to have a flow. You're more likely to have an explosive eruption. And so that's it. It's a situation where it's not necessarily a linear thing here where we have Hawaiian lavas, they always flow. We have rhyolites over here, like Yellowstone, they always erupt. It's not that clean, but if we want to simplify it, Hawaii more likely to flow. Hawaii has basalts more likely to flow. Places like Yellowstone actually has a variety of things, but what most folks think of for Yellowstone, right, has more silica, more likely to violently erupt.
And the
Although I want to ruin everybody's day, the most recent eruption of Yellowstone wasn't big. It was a lava flow. It was a basaltic lava flow. So I'm here to disappoint on that front.
uh, I think there was a I know it's going back a few years, but there was an explosive eruption in Iceland, wasn't there? Maybe, I don't know,
Yeah, and
2014
I'm
or
gonna. So that was Grimsvötn, and before that, I think the one you're probably thinking of is the apologies to everybody that knows how to say it correctly, but I'm gonna be brave here and let you record it. Eyjafjallajökull, which is the one that wrecked all the air traffic in Iceland. That was 2011, and so that actually had both explosive and diffusive phases.
so
And so
so it
that
had a
started
flow
off
as
with a lot.
well.
Yep.
Oh, that's interesting. Um, this that was before the time of you traveling to see these, though, huh?
Nope. I actually so you gave my dossier of failed careers and before coming into geosciences. And so I had a career as a graphic designer before I came into the geosciences, and then I took my first geology 100 class in 2010. And so that had happened kind of as I was coming into the science. And so I think another important thing to address with what is NSF funding, what is science funding, a lot of these kinds of fellowships, like the one that I talked about, kind of Frankensteining into what I do here in Hawaii now, a lot of that is kind of investment in scientists, right? How we develop, how we think. And so for me, being able to bring in those various aspects of my previous life as a designer and this kind of stuff, right? I don't think I wouldn't be sitting here talking to you if it wasn't for a variety of different NSF funded opportunities that allowed for me to figure out how I do science. I didn't come from a science background. I don't have a bunch of scientists in my family. I started off at a community college. And so for me, it definitely was a harder uphill to find my way into this profession. And so the science funding element that allowed for me to kind of figure out how I want to do science in a way that works with kind of how I think about science is I think for me the biggest benefit of those funding opportunities. Right? You're not just funding a study on, fish or echinoderms from your previous guest. It's not just funding, volcanoes. It's funding the people that do that work and bringing their skills into how that work gets done. And so because I had that graphic design background, it's such a help when it comes to doing some visual communication elements. Like, how do I draw this system that we can't see it? I mean, you can do some, you know, seismic imaging, try and get an idea of it, but a lot of science communication is visual, and so I feel really fortunate to have that element in there. And so you asked like, oh, there was the explosive and effusive one in Iceland, and so that I think was like the first eruption for me that happened when I was aware of, you know, volcanology as a science. There's a lot of folks that come into volcanology like, oh yeah, I was 4 years old. I saw a thing on Mount St. Helens. I was going to be a volcanologist. That was not me. That was not my path. I um so geology was my fourth major. I was originally a biomedical engineer, and then I met other engineers, and I decided that engineering wasn't for me. I married one though, so no shame to the engineers. I I have I cohabitate with one of you, so no judgment there. And then I transitioned into graphic design, and then I figured, oh, this is not for me. I don't like people. uh, The graphic design element was very like, oh, art is so much fun, but professional art is a different beast. Like, I like what you've done there with the logo, except I don't like the color and I don't like the font. Like, the logo is just the color and the font here. Like, you don't like any of it. That's okay, but that wasn't working for me. And then I went back for like K-12 education. And then I found, you know, geology, the research aspect of it. And so I actually didn't know anything about volcanoes until you know, started taking these classes. Although I met a volcanologist when I lived in Aotearoa, New Zealand. This is a fake job. This sounds like a fake job to me. And then when I went back to school for geology, my introduction to geology professor, her name is Dr. Bettina Martinez Hackert. She's like, oh, I do research on volcanoes. Like, I know two of you now. It can't be a fake job because now N equals two. And so that's kind of how I got into it. And so that Eyjafjallajökull eruption was like the first one that I experienced from from like a knowledgeable perspective of what I was looking at. So I went to Iceland actually in 2012 and hiked around, got to see all of that stuff, and it was incredible.
So that was sort of an important moment then in your early career as an undergraduate. Um, Now, uh, what when you take this data, is that now is that like openly available, the data that you're taking, or does somebody have to email you and get it? Is it I was curious about because like satellite data is an example sometime, or as long as it's not like protected for national security purposes or whatever is typically openly available. You can go download it at a website. Is that similar or
So there a lot of the data we collected alongside our USGS Hawaiian Volcano Observatory kind of counterparts, and so we participate. So a lot of the things that we publish are alongside them, and there is an open data requirement for like the government. And so the geochemical data that we have is kind of routine or not, we don't update the spreadsheet every day, but because it has to get reviewed, right? There is a kind of a checks and balances process, right? We want to make sure that taxpayer money is not going to fund like terrible science in this case. And so we have an internal review process for making sure that, all right, well, was the instrument calibrated? Like, are we conducting our, you know, checks here? Are we doing it in a way that is consistent with how we've done it in the past? Are these good data? And so we will release them as a data release before, so that folks don't have to wait for us to like publish papers, because as you heard, the volcano just keeps erupting. And so I'm not necessarily the fastest publisher. And so these data releases are a way for like that geochemical data that we're collecting to kind of make it out into the ether before the paper that accompany it or that will accompany it might. Another thing that if folks are interested in checking out monitoring data, not necessarily the stuff that I collect, but the stuff that gets collected here in Hawaii, You can go to the Hawaiian Volcano Observatory website and you can look at real-time data. And so you can see the tilt, you can see where the earthquakes are happening. You can see like the last week of earthquakes, the last month of earthquakes, tilt, that kind of stuff. And so there's a lot of data available, some of which I help collect, some of which is collected by the instruments here, maintained by the scientists at HVO. So the radar data that I collect, though, that is a little bit different because that involves a lot of processing. And so we are working with folks out of the University of South Florida. And so they are in charge of processing, that data. We have a paper in the ether right now. And so those data will be available once those papers come out, but those data are not like necessarily useful initially. It's not like, oh yeah, because when you are collecting radar data, right, there's the way that you might plot radar data, which is not the way that a human wants to look at it. And so there's a couple of steps you need to do. And so it's not something that, most people would, oh, let me look that up. Like, oh yes, I can convert from radar coordinates to polar coordinates, no problem. And so there are extra steps in that are not automated, and so we have to go in and like manually address those. And so that's going to have to wait for the publication.
Now, how you mentioned that you do some chemistry type measurements as well. How automated is that process? Is that fairly automated, or are you having, students do a bunch of chemistry type things and
So this this is not automatable work for a variety of reasons. So in order to collect the sample, right, a human at this point right now, based on where the eruption's been happening, a helicopter pilot and some other humans go land, collect the sample, bring it back to the lab. We put it in an oven. Then it comes out because we don't want to be incorporated. So when you grab a lava sample, it's really hot, and you don't necessarily want to put a flaming rock onto a helicopter. And so you also would like to quench it so that you can kind of prevent. So as you have lava flow cooling, you'll get slow cooling kind of crystals. Lava flows cool pretty quickly. So you want to kind of flash freeze it so you're not getting these kind of post-secondary crystals forming. Because we're not getting magma. We're not drilling in there, plucking out the magma. And so this is the closest we can get. And so somebody brings that back to the lab, somebody puts it in an oven so we can dry it out from kind of quenching it, and then somebody will crush it into a fine powder. There are things that we do here on islands because it's the Pono, it's the correct thing to do. We're not taking like, as much sample as we can possibly get, right? The way that Pelehunoamean volcanics are revered here is not the same as other places. And so we really focus on kind of small footprint, low impact sampling and processing because it's the culturally correct way to conduct work here. And so we take a little bit, like 10 grams of that, and crush it into a fine powder, and then we'll run it through a science box called the EDXRF, so the energy dispersive X-ray fluorescence. And so the students sometimes do it, HBO guys sometimes do it, faculty sometimes do it, staff sometimes do it. We have a really kind of nebulous and organic working group here. And so, hey, I got time in between classes, I'll put it in the oven. Or, hey, if you guys bring the sample, because I live up near the volcano, I could drive it in before I got to teach. And so it's whoever is here and able to do the work that does it. Very often it's the students, but sometimes it's who whatever warm body is in the lab that is part of the eruption response team.
how time sensitive are the samples? Like how long can you store them for before you have to do
Oh,
these?
indefinitely, right? A lot of the oldest material in the solar system that we have access to in terms of rocks turns out to be basalt, and so basalts are pretty shelf stable. But the speed at which we might process them depends on what's happening, right? Is the lava flow advancing towards a subdivision? We're going to prioritize that sampling. We're going to prioritize that sample. Right now, we have this kind of episodic. We'll have fountains for a day, be off for a couple days, fountains, right? Nobody's property is getting, threatened by the lava flow. And so if it happens on a weekend, right, I'm not going to ask students to, you got to come in and crush that on a Sunday. It's a holiday and your birthday, but you got to come in, right? That's not an appropriate use of their time. It's not respectful of that student. And so it's kind of holistically determined based on how many hours did we work this week? What do we need the sample process for? Is that sample as important as other samples? Right? Not every sample needs to get kind of processed through this geochemical machine uh, the day that it was collected. Although we have pioneered the system such that we have collected samples at 8 a.m. and we've had data by 2 p.m. So it's a well-oiled machine.
Now, you mentioned, of course, that I had originally asked you to come on for a specific grant, and you had an interesting story about that. Could you just briefly go through the story, if you don't mind?
Oh, absolutely. So right at the end of a PhD, mm, groveling for whatever job somebody will give you. And so you put everything out into the ether. I had originally written something called a Mendenhall Fellowship, which is like a USGS specific call for a specific, kind of, I want you to do some science on this volcano, or I want you to develop these kinds of techniques. And so there was a call for working on the 2018 eruption data. And so I'd written a Mendenhall for that, and it didn't end up getting funded. My buddy Brett got it, so he's excellent. He was my office mate when I came here too. But so I turned my failed Mendenhall into an NSF postdoc. So I threw that back out into the ether. But at the time, I didn't know that so the way that those Mendenhalls work, you don't necessarily know if that call got funded because they'll have like a bunch of them and they might interview people for all of them, but they might only, have money for this amount. So just because, somebody that got interviewed or somebody that was selected for it doesn't mean that that's actually going to be one that is then funded. And so all this happened. I knew I didn't get it, but I didn't know that my buddy had gotten it at the time. And so I had written something pretty similar to the original call, sent it back into the ether. I then ended up getting that fellowship at the University of Cambridge. And like during like the first couple of months of the pandemic, like the super depressing ones, I mean, they're all pretty depressing, but those first couple of ones, very, very, very non-ideal out there. Actually got an email. It's like, sorry, this NSF, like we don't have money for all of them. Thanks, but no thanks. And so my NSF proposal actually got rejected. And then I got a phone call from NSF. They're like, we need to talk to you like now. I did I do something? I don't did I do something wrong? Like I don't owe you guys any money. You never gave me money. And it turns out that they could fund like one or two that were like on the fringe. And so they needed an answer immediately. And so I turned my failed Mendenhall into my failed NSF, which ended up then eventually getting funded. And so because that project was actually really similar to the one my buddy Brett was doing, I didn't, we don't need two people working on the exact same stuff. And his bent was a little bit different too, because he had also been responding to some of the eruptions. He was a lot more kind of drone, aerial imagery, kind of 3D topography, um, video analysis focused. And so I took that opportunity to shift what I wanted to do to focus more on looking at the different ways that lava flows kind of channelize and form. So one of the things we did was we brought out yet a different radar, something called a ground penetrating radar. It's like kind of like it occasionally will look like a lawnmower. You have a transmitting antenna in the front, receiving antenna in the back. You pump some signal into the ground. If there are density differences, like imagine you have like concrete and then water, it'll see the interface between those sorts of things. It can do that with, different kinds of rocks and tephra and that kind of stuff. And so we brought the GPR out. So I was able to fund folks with that instrument to come out and actually left it here. And I think that that's one of the things that helped me get my job was having that instrument. Like I brought it in for my job interview. And so that's one of the things we did with it. Currently working on the growth of the main kind of eruptive center for 2018, the way that it grew. So we're focusing on that. Recently, I guess, I don't know, for me, this year is recently enough. And so we also had a paper where we looked at some of the data collected during the 2018 eruption. And so, right, lava is not just, if you look at lava flows and like, Star Wars and that kind of stuff, it's just like a blanket of fire like falling down a hill. Turns out that that's not super realistic. I'm sorry to disappoint your listeners. But very often, if you have lava flows that are kind of moving fast enough, they'll channelize, kind of like a river, right? With levees on the side or dikes, you know, whichever barrier you prefer. And those levees are not necessarily solid. And so I also used that fellowship to study how those levees deform. Because at one point we had an area that kind of backed up and ponded. And so you have kind of inflated blister of lava effectively. And when you break the blister, you are now kind of putting a different area in peril that's not like at the front of your lava flow. And so there are areas where maybe the sides of your lava flow are a little bit more kind of precipitous than others. And so I use some of that funding. I say we because I don't do singular science. Like I don't have science doesn't happen in a solo vacuum. And so we looked at how we could kind of track those the way that those levees would evolve in order to precipitate that kind of feature and that kind of event where you have a levee kind of catastrophically failing and sending a flood of lava kind of along the side of the channel and not necessarily down into the front. And so I use some of the funding for that, as well as using it to get out that terrestrial radar. And so I didn't really just focus on, my specific sciences as I was going forward. I really focused on supporting the network of people that I want to work with. And so I was able to bring out, I think, 6 or 7 people with the funding to come work with me out here. And so one of the things, right, as a postdoc, a lot of people will tell you like it's the most free scientifically you're going to be in your whole career because you're not, teaching, you're not doing all the other service kind of things, and they're definitely right. And so I wanted to bring that kind of feral energy into the government because I was stationed at the volcano observatory while I was there, and so I was able to kind of expand the instrument and instrument testing that we were able to do, still using that framework of I want it to be low impact, I want it to be culturally respectful, I want to be digging holes in people's backyards, massive holes that are, maybe not what they would want to do with the Ina, the land, that kind of stuff. And so I really invested in, bringing more people to work out here. And so some of those folks, one of them was a former undergrad student who's now at NASA. Their name is Yesenia. They're fantastic. And I also brought out one of my colleagues who does a lot of work in disability access for field experiences. And so that was one of the examples. I brought out one of my former professors at the University of South Florida to bring the GPR out here. And then I also helped bring out a grad student from the University of South Florida, actually 2 of them, to help run that bigger terrestrial radar, not the lawnmower radar, like the scanning radar. And so I really focused on kind of figuring out the logistics of how to get my collaborators out here with that work as well. And so when I think about, what did I do with that work? I invested not only in the science that happens in my local community, right? I live here. I am invested in us knowing what the volcano is doing because I can see it from my house. But I also invested in the careers of the people around me as well, right? Science doesn't happen in a vacuum. And so making sure that the ecosystem of my collaborators is healthy and operational was part of it as well.
And if you could, I think that you kind of covered a lot of the details there, but what was this money being spent on? Travel, salary, equipment, what was it being spent on?
So yeah, the way that those National Science Foundation postdoc fellowships work is I think my salary, so you get a salary. So I paid for my salary. That's pretty standard. And then you have like $25,000. So you get and you get about, I think it was $62,000 And so one of the things that, growing up not affluent, I was hoping scientists made more money, but it turns out we don't. So you just dispel that myth right out there. I have an almost 20-year-old car, although we are a two-car household now, but we still have a 20-year-old car. So one of them was salary. I so another thing that you probably heard about, folks have heard about in the news is like the overhead and that sort of stuff. Because I was working at an observatory and not a university, I didn't have to pay for the overhead. And because I was married, I didn't have to cover my health insurance out of my own salary. And so I had a little bit more money to be flexible with. And so I invested in a little bit of equipment, right? I had a pretty crappy computer, and so I wanted one that could run the programs I needed to process these data. So I got myself a computer. I went to a couple of conferences to network, right? I was on the job market, and so that is the pits of the post grad situation when you're groveling for jobs, you got to network and that kind of stuff. And so I went to conferences. I was really lucky because a lot of the field expenses that I would have had were mitigated by the fact that I was working at a volcano observatory. And so I was able to, I didn't have to rent a car to go in the field. I drove my own, you know, Honda Element dogmobile down to, the end of the block and wandered around. And so a lot of the expenses that a lot of people do have when they're conducting science, if you're doing place-based science, you really don't have that. I don't have to pay for a hotel. Just go sleep at home. And so when I would bring folks in to work with me, a lot of it would just be, all right, I'll get your plane ticket, but you staying at my house and we'll feed you. And so I spent, some of the money on bringing those collaborators in, a lot of it on shipping equipment in, because it's not getting things to Hawaii, very expensive. Like bread is like $8 a loaf. All the most expensive things are really big and very light. Potato chips, if they're not made on an island, forget it. And so a lot of expense went to shipping like the radars, the various radars over and um and that kind of stuff. And so that that $25,000, I feel like I really got a lot of miles out of it. I think we'll end up with, in terms of things that I specifically was driving the science for, like three publications so far. Three publications so far, working on some of the other ground penetrating radar data. And so I think we'll get 4 or 5 publications out of that grant. I established myself in a location where I am now an educator. And so I do a lot of place-based work with the data that I collected. Right, we ended up getting our own ground penetrating radar here at UH Hilo. And so my students are able to do some of that kind of work. And so we're able to, right, teach them there are ways of doing work in this landscape that are, more conducive with how we want to view our university, at least in terms of how we conduct science, right? We want to conduct culturally sensitive, respectful science. And so we focused a lot of that on, doing low impact activities. And so that GPR was a really good way for me to kind of sell that to my university. And so that's one of the things that we did. And so yeah, I really feel like I I would not have my job that I had now if I didn't have that NSF postdoc funding, like not even close. It's hard. Living in Hawaii is hard and trying to get people, like everyone wants to come to Hawaii, but not necessarily live here. There are a lot of folks that come to Hawaii and then they're like, this place is not for me. And so for me to, be able to live and work out here, I did live out here in 2012, 2013 as well, and so I already knew that I liked it. But I think that for me to really know that this is where I wanted to be was a huge um, deciding factor in my ability to get to stay here. And so that without that NSF funding, like I might not even be in science anymore, right? And so without that NSF funding too, like some of my students would not have had the experiences that they've had since I've gotten this job. Right? We've really, because I came from the Volcano Observatory to this institution, I brought a lot of those connections with me. Right? There was some strength and connections in the past because in 2018 the Volcano Observatory building got condemned, and so they actually were at UH Hilo for a little bit. but then they moved. But because I was working so closely with some of the scientists that had gotten hired kind of after 2018, I was able to bring that in with me. And so now my students are able to kind of work more directly with those folks. And so literally everything I do subsequent to that experience like would not have been possible without that funding. And so like every student of mine that gets to, you know, process some of these samples or use a GPR or that kind of stuff, like that is all because of this like little nucleus of funding at the beginning of my career.
I think that speaks very nicely to, importance of these kinds of funding these kinds of projects and launching careers.
I think also, right, and I know I said it earlier, but it's an investment in the scientists more so than in the, like good, good scientists will do good science. What constitutes a good scientist? There's not one formula. And I don't see a lot of representation for how I think about science or how my brain, you know, conducts, good science. Like I didn't see a lot of representation in how that worked for me. And so it took me a longer time to figure it out. But because I was given this opportunity to figure it out, it will then open the door for other folks as well. And there were funding opportunities through NSF that I got like small grants, a little Manini kind of grant before. And so really every single step of my academic career has been impacted in some way by having, National Science Foundation money, either through a research experience, like summer research, or through a rapid grant that sent me to Nicaragua, which was part of my, PhD kind of paper and my thesis and all that kind of stuff. And so really NSF has had a substantial impact in what I do. And now, right, every single student of mine is impacted by that first little grant that I got as an undergrad, and then by the second grant that I was kind of partially funded on in grad school. And now even bigger from this, this experience here with my fellowship, as well as the other folks that got to come to Hawaii to do that work. And so these things like it's it's an insanely good return on investment in my opinion. Like I might be biased as the investment, but I think it's important also to again to hit the fact that it is an investment in scientists. And so when you're out here and you're doing work and the volcano keeps erupting, like you can't just, well, this is what I'm doing. I was supposed to do this and this is what I'm going to do. It's not it's not the purpose of being at a volcano observatory. And so being able to dynamically switch gears and divide my time, like it was an investment in my ability to learn how to do that as well. And it turns out now when I'm teaching 3 classes a semester and the, eruption response and then doing service and then also doing other research stuff, those skills are very handy now in my everyday career.
Well, thank you very much for joining me. This was a great episode.
A little bit feral, but I hope it's what you wanted. And if it's not what you wanted, I'm glad that you enjoyed it.